All right. Hi, everyone. You guys can hear me? So today I'm going to be talking about AI in astronomy. And so you've probably heard about AI recently. Maybe you've seen a video of a cat riding a skateboard generated by AI, or you've generated, had it, manage your emails or write emails for you. But I'm really going to be talking about how we're using AI to deal with the massive amount of data that's coming from our telescopes. And it really is a big amount of data. And the whole goal is that if we have such a huge amount of data, we don't want to miss any discoveries that we could make in these data sets. And that's where using AI could actually help us. And so just to give you a little preview of what we're going to be talking about, we're going to talk first about, as I said, the mountain of data that we are getting, especially from two telescopes, the Euclid and the Rubin observatories. I'm going to take a zoom out and talk about human-driven discovery in astronomy, which is, just pouring through the data and realizing that, discoveries happen when you look at the data. And then I'm going to talk about how AI can help, deal with when there's too much data and too few astronomers to look over them. And I'm going to finish with just talking about how the new AI, that is AI that can understand language like ChatGPT, could potentially help us in astronomy, which is what my research is about. But just to start, I'm going to discuss this telescope right here. And this is the Euclid Space Telescope. It was launched by the European Space Agency. And since it's in space, it's not affected by rainy weather or city lights or mountains. It's fully in space, and so it has a full view of the sky. And what's really special about the Euclid Space Telescope is that it's going to image over 1 billion galaxies. And so on the right, you can actually see this is an image taken by Euclid. And you can just see all the galaxies in this image. Each of these points are galaxies, mostly. And a billion galaxies, a billion with a B, is just a fantastic amount of galaxies. It is, I'm going to show you, it's about 1,000 times more than any human has looked over, or any group of humans. And so the whole goal of Euclid with these billions of galaxies is actually to build a 3D map of our universe. And so not only do you get the positions of these galaxies, like on the image, but Euclid is also measuring their distances. And so with a billion galaxies, you can build this very large, or the largest ever map of our universe, which will help us to better understand how it's structured. And so this is just a glimpse of a massive amount of data that is now coming our way. Another telescope that just recently turned online and is now collecting data is the Rubin Observatory. And so this is on a mountaintop in Chile. And what's special about the Rubin Observatory is how fast it scans the sky. It has the largest camera ever made, and it's also the fastest telescope in which how quickly it scans the sky. And the whole goal of that is to image the entire southern sky every 3 days. And you're probably wondering, okay, what's it matter if a telescope is fast? Well, if we get a photo of each point in the sky every 3 days, what you can do is you can look at how the sky is changing every 3 days. And so if you look at this photo, this is one photo of a galaxy, and then a photo of the same galaxy taken 3 days later. What you'll notice is that there's a difference. There's a bright, what looks like a star that appeared in the second image. And what that actually is it's a supernova. And so supernovae are the extremely bright explosions that happen at the end of a star's life. And since the Rubin Observatory is scanning the whole sky every 3 days, it's going to produce, or it's going to discover a whole lot more supernova than we've ever imaged before or ever discovered before. And this, massive amount of data, once again, is going to be way more than any one human can look over. And so actually, let's zoom back a bit and think about how discoveries have been made in astronomy so far. And I'm zooming all the way back to the early 20th and late 19th centuries, when there was when a computer, as you know it wasn't a machine that sits on your desk and requires electricity, but it was actually a human. And what they would do, these computers, is they would pore over math calculations or data in order to make discoveries. And this particular group of computers, the Harvard computers, were at the Harvard Observatory and looked over what's known as stellar spectra. And so stellar spectra is essentially the brightness of stars over color. So a star can be brighter or dimmer at certain colors, and that can actually tell us about their compositions. So what the star is actually made of, whether it has hydrogen or helium or silicon. And what these computers, which was actually mainly women, what they would do is they would classify these stars based off of looking at their spectra. And they were so adept, and they perfected this art, or this science in this case, of classifying the spectra that they were able to get through 5,000 stars a week. And not only did they do that, but by looking at the data, they were able to make incredible discoveries. For example, Fleming and Cannon revolutionized the way that we classify stars. And they built the classification scheme that we still use today. Leavitt found that certain pulsating stars, which were stars that grew brighter and dimmer over time, the Cepheid variable stars, had their brightness related to how fast they pulsate. Payne found that stars were made of hydrogen and helium, which was an absolutely massive discovery that could not have been made unless you had humans looking at the data. And so this is, something that is essential. And the modern day equivalent of humans looking at a ton of astronomy data, all the data coming from these telescopes, is this website actually called Galaxy Zoo, where no longer can you fit the teams in one room to look at all the data coming from these telescopes. But in the modern day, we no longer have 5,000 stars a week. We have millions of images of galaxies like this one. And essentially what this Galaxy Zoo website is it shows you an image of a galaxy. And you can choose, is this galaxy, is it smooth? Is it a disk? Like, does it have spiral arms? And in this case, this galaxy has spiral arms. So you would choose this option here. And then after that, it would ask you, quite a few other questions, like how many spiral arms? And with this website, over 16 years, volunteers and experts have classified 1.5 million galaxies, which is, a substantial amount. It's actually revolutionized like how we actually study these galaxies. For example, this data is essential to understand how these galaxies form. And so once again, looking at the data has also led to discoveries in this case as well. So this is a Dutch school teacher named Hanny. And while doing Galaxy Zoo, she was actually able to find this very interesting phenomenon, this glow, this green glow under this galaxy. And noticing that, she brought it up to professional astronomers who pointed the Hubble Space Telescope at it and found that this is actually, you could think of it like an echo that came from a very active black hole in the center of this galaxy that was giving off a lot of light. And then it turned off, but the light was still traveling and interacted with this gas that led to this green glow. And so just by poring over millions of galaxy images, you get amazing discoveries like this one from looking at the data. And so clearly humans are essential for making discoveries in astronomy. And I don't think this is going to change. I think that always the important discoveries in astronomy are going to come from humans looking at the data. So the question is how can AI help us? Well, the reason why I'm turning to AI and why I think it's essential is that no longer can we have humans, volunteers, or experts look over all of the galaxies that we're collecting. As I said, like Galaxy Zoo looked at 1 million images over 16 years. But Euclid is going to produce 1 billion. And so we either have to find 1,000 more humans, or we're going to have to look at all this data over 1,600 years rather than 16 years. And so the way that AI can help is it can filter down these massive data sets into the most exciting examples that we can then look at as humans. And so, okay, I've said AI a ton now, AI. But what actually is it? So I'm going to use an example to kind of introduce us into what I mean by AI. And to do that, I'm going to talk about, here's an image of a dog and a cat. This is actually my dog and my girlfriend's cat. And my question is which one is the dog and which one is the cat? Now, it's an easy question for us. The one on the left is a dog, the one on the right is a cat. But how do you know that? How did you figure that out? For me, we all grew up, we started as babies and we grew up and our brains developed to learn which one was a dog and which one was a cat. And our brain picks up on patterns like, you might have these pointed ears. Well, that would indicate it's a cat, or like these feline pupils. We all understand these patterns, but how would you go about teaching a computer these patterns? You could write programs, you could write an algorithm with rules to say, oh, if you see a pointed ear, it's likely a cat. However, then you have to teach it how to recognize what an ear looks like. How do you do that? Oh, well, you have to teach it what like an edge of an ear looks like. And it just becomes, an absolute mess. Like there's no way that you're going to teach it all the rules. And so what computer scientists did is they actually were inspired by how our brains learned. And our brains are actually made up of a bunch of what are called neurons. And so our brains, they weren't taught these rules about, what an edge is and what a pointed ear is. It learned from our whole lifetime of experiences. And so with a type of algorithm called a neural network that was modeled off of, human brains, or all brains, I guess, they were able to develop an algorithm that was essentially just a ton of mathematical operations that you can modify automatically based off of training it with a number of examples. And so what you can do is you can give it an image, say, of a cat, and you could have it predict whether it's a cat or a dog. And if it predicts wrongly, if it predicts a dog, what it can do is during the training, it's called, is it can automatically modify its internals so that the next time it sees that image or an image like it, it predicts cat instead of dog. And so it does this automatically. So I'm not going in there and modifying the internals. You just give it 1 million images, half of cats, half of dogs during the training, and it's able to tweak its internals such that it can learn to differentiate between a cat and a dog. And it works for galaxy images too, and a number of other things. So for example, if you have, a million images of a smooth galaxy versus a spiral galaxy, it can learn, these neural networks can learn to recognize the difference. And so why is this useful? I'm not going to, maybe classifying spirals versus smooth galaxies is useful, but it's also very useful to find needles in haystacks, I'm going to say, because there's going to be very rare objects in our data sets, like this object here. It looks really crazy, but what essentially this is it's a gravitational lens. And how that works is you have a very massive galaxy in front of another galaxy. So there's a galaxy behind it that should be blocked. We shouldn't be able to see it because there's a galaxy in front of it. But Einstein actually found that light is bent by gravity. And so the gravity of the galaxy in front of it is actually bending the light, like you're seeing here, of the galaxy behind it. And so it creates this ring. And so this ring is actually the galaxy that's behind this one in the center. And so these gravitational lenses are actually really rare. But what we can do, and what actually a astronomer at University of Toronto did, Mike Walmsley, is he developed a on top of Galaxy Zoo, a volunteer campaign to label whether an image is showing a gravitational lens or not. And then by doing this for a ton of images, they collected a training set to then train a neural network to distinguish between a gravitational lens or not a gravitational lens. And then with this neural network, they were able to run it on 1 million galaxy images. So this is more than, it would take a team of humans like 16 years to look over 1 million images. But since they trained a neural network to classify whether an image is a gravitational lens or not, they were able to run it over this large data set. And so what they found is they turned 1 million images, galaxy images, and whittled it down to, 1,000 that the neural network predicted was a gravitational lens. But they didn't stop there because, you can't trust blindly what comes out of a neural network when it comes to predictions. So they had to show that to experts and volunteers. And then from those, they were able to find 500 actual images of gravitational lensing. And 500 is a lot. Before this study, there was only around 1,000 that were known. So this is a 50% increase. And what's amazing is that this was off of Euclid data from the Euclid telescope, and that just started its mission. And so if they keep the neural network like the exact same and run it at the end of the mission for Euclid, after it's been taking images for like 10 years, they predict they're actually going to be able to find 100,000 gravitational lenses, which is 100 times more than what we know now. And so this is actually going to be useful for studying stuff like dark matter, which is an invisible form of matter that actually is creating most of the gravity that is bending this light, which is really amazing. And so I'm going to go over a few more examples about how AI is able to help us sift through the massive amounts of data that's coming from these telescopes. And another example here is actually finding exoplanets. And so exoplanets are planets that are around stars that are not our own. They're in other solar systems. And one way they are typically found is by having a planet. If you're very lucky, it will, as it orbits around another star, it will pass in front of the star. And actually, we'll see this by the star dimming for a certain period of time. So this is on the y-axis, this is the brightness of the star, and then this is time. And as you see, as the planet passes in front, it dims, and this is called a transit. And this looks amazing in this plot, but this is just an animation. In the real data, it's actually really difficult to see. There could be lots of dips in this. So this could be a source of many planets. And so we actually already have algorithms, and we already have humans to look over all of the data that we have of these, the brightness over time to look for these dips. However, there was this one team, and this is Christopher Shalu, who decided to look over data that was already analyzed. And so what they did is they built a neural network, and they trained it to try and find these dips and brightnesses, to try and find new exoplanets. And they ran it on data that was already analyzed by humans and all previous methods. And what's amazing is that they were able to find a new planet that everything else had missed. And this planet was actually found and is known as Kepler 90I. And it was already in an extremely busy system. So this system already had 7 different planets around this star that were discovered by other methods. But with their neural network, they were able to find one more planet in the system, which actually at the time tied it with the most amount of planets that we know in one system, tied with our own solar system. And so I actually really love this example because it shows that AI can be used to ensure no discovery goes missed in data that we might have already looked over with our current methods. Okay, back to the Rubin Space Telescope, or sorry, the Rubin Telescope. It's not in space, it's on a mountain in Chile. It's, as I said, is scanning the whole sky every 3 days, and it's finding stuff like this supernova. The only issue is that, it's anytime it finds a change in an image, it alerts an astronomer. And the only issue is that this is going to happen 10 million times a day. So, clearly you'd be up, you wouldn't just be up all night. You'd be up for the rest of your life looking at all this data. And so once again, we need a way to triage this. We need a way to make it so human time is well spent. And there's a lot of things that could be causing a change in an image. For example, it might not just be a supernova, it might be a satellite that passes through the image. It might be an asteroid. It might be a star that just pulsates, it changes in brightness over time. And so this team has actually built a classification method using AI to classify these changes into all these different categories, including many different categories of supernova. And so this makes it so that humans don't have to go and classify 10 million alerts per day. And at the end of its 10-year mission, this is actually going to lead to 3 million supernova that will be discovered by the Vera Rubin Observatory, which is a lot higher than less than 100,000, which is known today. We're going to find 30 times more supernova just from this telescope alone. And so this is going to greatly improve our ability to understand the dynamics of these stars at the end of their life. So the interesting thing here is that all the examples I gave you, like the gravitational lenses, the exoplanets, the supernova, are stuff that we know is going to be in the data. Like we know these exist. But the most interesting discoveries in astronomy are for unknown unknowns. And so these are things that we don't know exists, completely brand new stuff. Like I showed you about, that cloud of gas that Dutch school teacher Hanny found. just randomly looking at the data. Like this was something we didn't know existed. It was a brand new discovery. And what's really cool is that there's actually an AI algorithm out there that can try and look for these unknown unknowns. And it's called anomaly detection. And the event, essentially the theory behind it is you're looking for the least normal galaxy in this case. And so this is a team led by Michelle Lochner out of South Africa. And they were looking at images of galaxies in the radio wavelengths. And this is what a normal galaxy looks like. It's very boring. It's just a circle. But what's cool is that they were able to develop a AI algorithm that could find the furthest from normal, the most weirdest looking galaxies out there. And this is one of the ones that they found, which looks really crazy. And so they call this one Sauron for some reason. It looks like the eye of Sauron. It's very creepy. And what's amazing here is that it looks like actually the galaxy, I think, should be in the center here. And what's bright is you have this odd, radio circle, this circle of radio emission around the galaxy. And they believe, they're still investigating, but they believe it's caused by potentially a merger of two black holes in the center of this galaxy that sent out a shock wave of energy that then caused the outskirts, of the galaxy to be very bright in the radio wavelengths, which is really cool. But there's an issue, which is that actually, if you're looking for the least average or the least normal galaxies, you're going to find ones that look like this, which is not aliens shooting a laser beam through this galaxy. It's actually just a satellite. But to an AI, this does not look normal. This looks absolutely crazy. It's clearly not an average looking galaxy, and neither are these two. But the thing is that this algorithm, that's all it does is it finds the least average looking galaxy. It does not know that this is actually scientifically uninteresting. It's just a satellite, it's not a brand new discovery. And so when you actually use this algorithm, you just get a ton of these, what are essentially just, issues with the telescope or satellites going in front of it. And so it's not able to recognize that this is not a scientific discovery. And so another limitation with AI, or these neural networks specifically, is that they're known as black boxes. And by that, I mean that we actually don't know how they work, which is really funny. As I said, they're not made with like pre-programmed rules that looks for, the sharp ears of a cat to determine if it's a cat. They don't have any built-in rules. And so, we actually have a very difficult time knowing how they made certain decisions. And so this is actually where I'm excited about stuff like ChatGPT, models that can actually understand language. Because if it understands language, then instead of, if I wanted to understand how you knew, like whether the image was a cat or a dog, I wouldn't, do neurosurgery on you. I would actually just ask you first. So in this case, with a model that can actually talk, with language, you might be able to ask it how it made a decision. And so just introduction to ChatGPT. ChatGPT actually is a neural network, the same ones that I've been telling you about, but it was trained to complete sentences. And so this is an example. Abigail went to the bakery to buy blank. And so we know that the answer is bread and not a ceiling fan. Um, but when you're starting out, like when ChatGPT was not yet trained, it did not know that you buy bread from a bakery and not a ceiling fan. And so it was essentially trained on sentences like this that was scraped from the entire internet. So Wikipedia posts, blog posts, stuff like this. They gave it the first parts of a sentence and asked it to predict what the next sentence or what the next word in that sentence would be. And so by training it like this, it actually learned how to have conversations. It learned, facts about our world. And so not only that, but it was also trained on astronomy papers and posts from NASA. And so it actually knows a lot about astronomy. And it also understands images as well. Because, there's plenty of images on the internet that was included in its training. And if you have, for example, an image on a NASA post or a paper where you have an image and then a caption underneath, it's able to learn stuff like that this shows a galaxy surrounded by tidal streams and not gravitational lensing. I'm going to go into what tidal streams are in a minute. But this ability is really cool. And so like with traditional AI, like the neural networks I was telling you about, that's able to classify whether something, what type of galaxy something is. Like, for example, it's able to find, oh, this is a merger between two galaxies. But ChatGPT is able to write a full description and maybe even tell you if it's scientifically interesting. And so it's able to say, oh, this is an interacting and merging galaxy system, specifically a late stage major merger between two disk galaxies. And that's actually, it's actually pretty good. And so I was able to use this in my own research where I'm trying to figure out how this ability can actually help astronomers. And so what I did was I had it, ChatGPT, describe galaxy images. Not just a few, but I actually had it write descriptions for 300,000 galaxy images. And I found that the descriptions are, actually quite good at describing what's in the image. For example, like this one says, there's dual luminous nuclei, which is true. There's two nuclei in this image. And now what can you do when you have 300,000 images and 300,000 descriptions is you can actually make a Google Images, but for images of galaxies. So I actually did this. I made a search engine where you can search up stuff like edge-on galaxy with dust lanes, or a face-on spiral with a ring-like structure around a core, or a single red galaxy, or a star-forming galaxy. And we actually were able to build a search engine for 20 million images that no human has ever looked at. And with this search engine, this like Google Images for galaxies, you're able to do these text-based searches for phenomena that you're interested in, which is totally different than what happened before. If you were very interested in edge-on galaxies, what you would need to do is you would need to get a ton of experts together to label what galaxies are edge-on or what are not by looking at thousands and thousands of images, and then you need to train a neural network, etc., to then go and classify a huge amount more. But now you can just search it with text. And we actually made this into a website that you guys can actually use. And it's actually, live. You can search 20 million images. You can search up aliens. You won't find anything cool. I've tried. I've not found any aliens, unfortunately. But it's just really cool what you can go and do with this search engine, which was not possible before, all because ChatGPT was able to write descriptions for these galaxies. And so why did I do this? Well, our group is very interested in a particular type of galaxy, or particular type of galaxies, which are ones with these tidal streams. And essentially what they are is they are a larger galaxy in the middle, and then a smaller galaxy got a little too close and was torn apart into a stream of gas and stars. And so essentially how this happened is you have a larger galaxy and a smaller galaxy. When it gets too close, the strong gravity of the larger galaxy is going to pull apart the smaller galaxy and rip it apart into this stream. And why we're interested in this phenomena is actually that the gravity that is coming from this galaxy is what forms it into this stream. It's pulling on each part of this stream in a different way. And this stream of stars actually follow what is essentially an orbit around this larger galaxy. And what's cool is when I say the gravity of the larger galaxy, you might think the gravity is caused by all of the stars in this larger galaxy. But what's amazing is that most of this gravity is actually coming from dark matter, which, as I said earlier, it's a type of matter that we cannot see. It's invisible, but it has a very strong gravitational pull in this galaxy. And so by looking at actually the shape of the streams of the ripped up galaxies, you can actually understand the gravity that is pulling on it, the gravity caused by this dark matter. And so there's a PhD student, Jacob Niebauer, that actually was part of developing this method to understand, how to study the shape of dark matter based off how these streams are curved. But the issue is that Jacob here needs a ton of images of galaxies of streams, and there has been no neural network out there that could identify them until now, because we found that ChatGPT could actually identify it just right off the bat with no additional training right out of the box. And so with my data set of galaxy descriptions and with my Google images for galaxies, I was able to just search up galaxy with stream in my search engine. And through a lot of looking, I was able to find all these examples of galaxies with streams, which we can then use to try and understand the dark matter in these galaxies. And so, here's the big picture. We're getting a ton of data from all these telescopes. And I believe that, and I'm incredibly excited, especially for stuff like ChatGPT, that can help us understand and make sure that no discovery goes missed in this mountain of data from Euclid and Rubin. And I really want to emphasize that discoveries in astronomy are found by humans. And so I think that going into the future, I've shown the massive amount of data that we're going to get. I think that humans are going to be way more in demand in the future in astronomy than they are now. Because what AI is going to do is it's going to help us, whittle down all this data to only the most interesting ones that we're still going to need a ton of humans to look over. And so I really emphasize this by showing all the images, all the faces of astronomers and volunteers throughout this presentation that are going to be in demand for looking over this data and also, developing these methods to help us understand it. And so I think that this is how we make sure that no discovery goes missed in this mountain of data, by having, humans using AI to whittle it down to the most interesting examples for us to look over. Thank you so much.
That was an amazing talk,
Thank
and
you.
thanks so much. Um, I'm just wondering. I'm mindful of the data set that can actually come from audio, like radio signals too. For example, you're talking about the mountain of data
Mm.
that is out there for classifying galaxies and all that. Um, has SETI made use of? I can see a great potential in looking for um, possible and classifying certain signals that might come from out there. And I know that SETI had a program, SETI at Home, I believe, and that you could download a portion of that program anyway, and they would give you data and your computer would work on it. Well, now we have AI,
Right.
so perhaps they could, or maybe they have already made use of it. You know, any maybe they have done that. I'm not sure. It sounds like a great thing for them.
Yeah, totally. I love SETI. Like it's a absolutely great mission. So for those who don't know, SETI is a search for extraterrestrial intelligence, and essentially they use radio telescopes to look for signatures from potential alien civilizations, which is really cool. And I know for sure that they are using AI to try and sift through this data, potentially stuff like anomaly detection, because we don't know, what the aliens are going to send, obviously, if they do send anything. And so what you're going to need to do is you need to be able to differentiate just random radio from natural causes from, what could actually be stuff from a civilization. And so actually next AstroTours, we have a talk from a new student here at Pynchon on technosignatures, which are exactly what you're describing, like signatures from alien civilizations. So you got to stay tuned for that.
Oh, I'm coming to that one.
Oh yeah.
Thank you for the
Thanks.
plug, Nolan. That's great.
Yeah.
Thank you.
No worries. Thanks.
Any other questions?
There's a lot of hands over here.
Okay, we'll go over
Yeah.
here.
Excellent talk.
Thank you.
I'm a little bit in the field, but in a totally different area in commercial applications for AI. One of the things that I've been doing is trying to get people to understand that it's a very broad area. I like to get people to talk about it as being, as you're showing, it's augmented intelligence. That's what we're using it for.
Sure.
One of the things that I'm curious about with the aspect with SETI, and certainly I'll be at the next session. You've been needing to have training data sets.
Right.
And of course, one of the problems with that is that what would we do if we said, hey, we want to try to find Dyson spheres? Do we say, hey, this is what we think it will look like? So let's train you on that and then go searching. Can you comment on that?
Yeah, totally. So just for context for others, so Dyson spheres are essentially a theory that an alien civilization could wrap their star in essentially solar panels to collect all the energy from that star. And actually, they can be detectable theoretically, because what you can do is you can look for, you wouldn't be able to see the star because it'd be covered by this sphere of solar panels, essentially, or metal. But that metal should still, produce a signal in the infrared because it should be hot. And so if you want to go out and look for them, my search engine won't be able to find it, unfortunately. But what you can do is you could try and simulate it and use the simulated data for what you think it's going to look like to then train something like a neural network. And so if it can work in the simulation, it should be able to work in reality. However, in a lot of cases, this actually becomes much more difficult because we have to be able to simulate, what it would look like almost perfectly to do it this way, which is a big issue, and certainly being worked on. That's a great question. Thanks.
Any other questions?
That was a very interesting talk.
Thanks.
Now I asked this question as both an amateur astronomer and I'm a member of the Royal Astronomical Society of Canada.
Nice.
Now, considering the popularity of AI and citizen science and amateur astronomy, how can AI promote the application of the ability for the ordinary folk to assist in studying galaxies, considering how accessible AI and the field of amateur astronomy is nowadays?
Yeah, I think so. I'm super biased because I like AI, but I actually think that, especially when it comes to language models like ChatGPT, I think can be incredibly useful for lowering the barrier of entry for people. For example, like the stuff we do in astronomy, we're using some data sets that are really locked away in some obscure website. And you need to, have some understanding of how to use the website to actually get the data. And maybe you might need to write code to actually get the data. And the data might just be images of galaxies, for example. But with stuff like ChatGPT, even if you, are not an astronomer, you can actually ask ChatGPT, how could I potentially get these galaxy images from this telescope? And it could actually try and get that data for you, which actually built this application called Chat Gaia, which actually does exactly this. You can just chat with it and say, hey, I want all the stars in the Large Magellanic Cloud, and I want you to plot, the color versus brightness of these stars. And it's actually able to use ChatGPT to actually get you that data and plot it. And so I do think it lowers the barrier of entry when it comes to this kind of research. And then also you can ask it what it thinks about, you can ask it questions for you to better understand what you're actually doing with that. So it's a great question. Yeah.
Okay, I think we'll stop questions for now, but I will note that Nolan will be around for a little bit after the talk. We just wanted to get to introducing the tours and the activities, so we have time for that. So I'll let you describe that, Abigail.
Thanks.
And thank you again to Nolan.